Okay, let's take a look at a topic you guys haven't really seen before very much. It's called enthalpy. Okay, now enthalpy is another word for basically heat transfer within a reaction. Okay, and a lot of these values have been measured and documented for many different reactions. And what you're going to see is, say, a balanced equation, and then there'll be this delta H. Remember, delta means change. So this is like change in heat. And this number is basically telling us if this reaction in these perfect amounts were to take place, it would produce 1,367 kilojoules. That negative right there means it's going to be exothermic, so it's going to release that much energy. If that were positive, it means have to absorb that energy in order for this reaction to happen. Okay, so what we're going to do is we're going to start working with some of these delta H values, some of these enthalpy values, and it's kind of, you aren't going to really have too much trouble with this because we can sort of treat this as though it's part of this reaction, and when we do deal with some of our stoichiometry relationships, this is just going to become part of that. Okay, so let's take a look at how we would use it. And this first question says, how much heat is produced by 100 grams of ethanol? So up here we've got ethanol burning in oxygen, nice combustion reaction, it's all balanced. Let's start the way we normally would. We're going to take 100 grams of ethanol, C2H5OH. Okay. And normally what we always do is we turn that into moles, and that doesn't change. Moles of ethanol, C2H5OH. Okay. And down here would go grams. We would get its mass from the periodic table, C2H5OH. Okay. Now once we have the moles of one of these things within the reaction, just one of those items, we can relate it directly to the ratio of energy that it produces because we're assuming we have enough of the other stuff to make this reaction happen. So right now what I'm seeing is 1,367 kilojoules. 1,367 kilojoules are going to be produced in a perfect reaction by 1 mole of ethanol. Okay, let's put 1 mole C2H5OH down here. Now if you think about this, I know I didn't put the negative in here because I'm just kind of interpreting that it's getting released. And so that negative, I could just kind of ignore it for the time being because I know what's actually happening is it's letting this energy out. This energy is going to get sent out into the atmosphere, into the surroundings. But if I look at what I did, I turned grams into moles, and then I went straight to energy instead of turning it into something else within the reaction. We can treat this as though it's kind of part of the reaction. If I look at my units, moles here cancel out, grams here will cancel out. All I've got to do now is figure out the molar mass of ethanol. Okay, and if I add that up from the periodic table, I get a value of 46 grams per 1 mole. So basically I can figure out exactly how much energy is going to come from this reaction with any amount of some substance I'm starting with. All I have to do is use this ratio compared. Now why is this right down here 1 mole? Double check that. That's because this up here was 1 mole. So you look at your balanced equation. Okay, now if I go through and solve that, I'm going to end up with 2,972 kilojoules of energy. Okay. Now let's take a look at going a different direction. You can also use energy as sort of a target amount. So in this one it's saying if we're trying to produce 5,000 kilojoules of energy, how much oxygen would be needed in order to make that happen? Okay, so now we're starting with a certain amount of energy we want to target, we want to make, and work our way backwards to how much of a reactant might be necessary for this to occur. So I'm going to take 5,000 kilojoules. I'm going to try to relate that to moles of oxygen, and then convert that to grams of oxygen because that's something I can actually measure. So kilojoules is going to go down here. Okay, we just drag it down. Moles of oxygen goes down here. And this looks very similar to this. It's just kind of in reverse. So I'm going to look at this and go, all right, in this reaction I have 3 moles of oxygen. And that is 3 moles of oxygen would produce 1,367 kilojoules of energy. And then I go back to moles to grams. I know that comes from the periodic table. Oxygen weighs 32 grams for every 1 mole. So if I solve this, it's going to tell me that I need 117 grams of pure oxygen gas with enough ethanol in order to produce the 5,000 kilojoules of energy we were trying to make as our target value.